Given matrix A, we need to find the eigenvalues. Eigenvectors correspond to the eigenvalues. We check whether the matrix is diagonalizable and find the power. To find the eigenvalues we find the roots of the characteristic polynomial. Is say P lambda is a determinant of this matrix. Minus lambda, minus lambda, minus lambda. Let's do cofactor expansion over the last row. We will have 2 0 here. So lambda determinant of this matrix plus 6 1 minus lambda, so what 1 plus lambda, lambda minus 4 plus 6. Oof, we need to take it, compute it anyway. Lambda square minus 4 lambda plus 1 lambda minus 3 lambda plus 6. Okay, lambda square 3 lambda plus 2, right? 1 minus lambda, so it's minus 1 minus 2. Lambda minus 1 times lambda minus 2. Yeah, here's how I compute it. Lambda here, right? It would be something plus something equal to minus 3, and that something, say A, times B would be 2. So what we have should be A should be minus AB should be minus 1 minus 2, right? So the sum will be minus 3, the product is 2. That's why I can factorize like this. Yeah, just a way how I compute it. So what is this? Minus lambda minus 1 square lambda minus 2. Oof. So the roots are eigenvalues. Lambda 1, lambda 2, 1. So let's say 1 has algebraic multiplicity of 1 is 2, and lambda 3, 2. So algebraic multiplicity of 2 is 1. Okay, now we find the corresponding eigenspace, right? Lambda equal to 1. In fact, lambda 1 equal to lambda 2, say equal to 1. The corresponding eigenspace correspond to 1 is just a new space of A minus 1i. What? Just find it. So A minus 1i, just replace this matrix, right? Minus 1. A minus 1i, minus 1, minus 1, minus 1. 3, 2, 1, 3, 2, 1, 0, 0. No. Okay, let's do some elimination. Oh no, it's just 1 minus 1 0 0 0 0 0 0 0. So what is the corresponding system? x1, x2, 0, x3, right? That's all. So what do we have? x3 can be chosen arbitrarily, say alpha, because whatever alpha is times 0 will be 0. x2 say beta, and x3 say equal to x1 equal to x2 equal beta. So eigenspace corresponding to 1 space of the matrix A minus I is a set of vectors beta, beta, alpha spanned by, okay, let me do one more step, beta 1 1 0 0 0 1. So this is a vector subspace R3 spanned by two vectors 1 1 0 0 0 1. Okay. Dimension of this space 2. Correspond to 1. Dimension over R, in fact. So what does that mean? The geometric multiplicity correspond to 1, 2 is the same as algebraic multiplicity, right? Let's do, okay, so we can claim something else. Okay. Eigenvectors correspond to lambda 1, lambda 2 equal to 1, correspond to 1. Okay. Pick vectors, so any vectors, or I can write a set of eigenvector of all I correspond to is a known space A minus I, that space. Take out vector 0 because 0 cannot be eigenvectors, that's all. So this, everything in this spanned by these two vectors. And so any non-zero vector spanned by these two vectors. So which is a vector of this form, right? Where alpha and beta are non-zero at the same time. So cannot be alpha equal to beta equal to 0. What is the part C? We didn't finish. Part B for lambda 3 equal to 2. Lambda 3 equal to 2. So we have this matrix. Eigenspace correspond to space of A to I, A minus 2 I, A minus 2 minus 2 minus 2, 2 2 1 3 3 1 0 0 minus 1 0. Okay, so this matrix is 2 minus 3 0. Okay, let me do our Gauss elimination so let's do Gauss elimination 0 0 0 1 minus 1 minus 1. And now let's withdraw 1 minus 1, 0, 0, 0, 2, minus 3, 0. What else we should do? Row 2 minus 2 times row 1. Put in row 2. Minus 1, 0, minus 3, minus 2 times minus 1, minus 2 times 2, 0, 0, 0. I think we good. Okay, let's do just one more. 1 minus 1 minus 1, 0, 1 minus 2, 0, 0, 0. Let's just plus. So this is what I do. We just minus row 2, put it in row 2. So it, in fact, this means that minus 1 times row 2. Now just put row 2 plus row 1. Put it. Sorry, you should even write row 1 plus row 2, row 1. 1, 0, minus 3, 0, 1, minus 2, 0, 0, 0. System is x1 plus 0, x2. 3x3 is 0, x2. I can delete this, x3, 0. So what? Let's say x3 equal to alpha. x2, 2 alpha. x1, 3 alpha. So the eigen space correspond to 2 is space correspond to A to I. Set of vectors, you can write x1, x2, x3, alpha 3, 2, 1. Okay, so what? This is spanned by 3, 2, 1 transpose. Dimension of eigenspace correspond to this is 1. So this is geometric multiplicity of 2 is 1. Right? It's the same as algebraic multiplicity. And here also it's the same as algebraic multiplicity of 1, right? So what does that say? Let's say that the matrix A is diagonalizable, and A can be written as, say, what's what I write? P, D, P inverse. D, the diagonal matrix, lists all the eigenvalues on the diagonal. So the rest are 0. P, the first column vectors is a eigenvectors correspond to eigenvalues 1. So what is this? This is the two vectors 1, 1, 0 and 0, 0, 1. 1, 1, 0, 0, 1, and the last one is corresponding to eigenspace eigenvalue 2, so 3, 2, 1. P inverse become P. And what? The last part is find A to power n, right? A to power n is P D P inverse power n. P D P inverse P D P inverse D P inverse. We call all of those terms P inverse and P cancel out. So this is P D power n P inverse. And D power n diagonal matrix n, it just is 1 power n. And 1 power n is just 1. Right, that's all. And multiply P inverse. P inverse you compute it explicitly. Yeah. So basically it's this.